Hey Mr. Lee, today I will be discussing odd and even functions and how to identify them based on several key features, whether that's using symmetry, algebra, and why those patterns happen. Then we'll also look over how to prove whether a function is odd or even using definitions. What is an even function? Well, to prove that something is an even function, it must have these three key features, or it doesn't have to, but you'll see what I mean. So, even functions have line symmetry over the y-axis. So, if I were to split this function in half by the y-axis, like this, you would see that both halves are pretty much the same. If I kind of flipped the side over on this side, it would be the same thing. The exponent on the terms has to be even. As you can see, this is an even number. And even functions also may have a constant term, meaning x has an exponent of 0. Now, for an odd function, it must have point symmetry about the origin, which is 0, 0, just right here. Oops. And then you'll see when I rotate this function by 180 degrees, and as you can see, it is the same as the original function. That's how you can tell it's an odd function. And then you can see that the exponents are odd. I'll show you later, but for odd functions, there are no constant terms. Okay, so now I'm going to show you how to prove whether a function is even, odd, or neither. So an even function is f at x equal to f minus x. F minus x means replacing every x value with minus x. So it doesn't change the output value, it just changes what's inside of here. So for odd functions, negative f at x is equal to f at negative x. So negative f at x means multiplying the entire function by negative 1. This means the outputs are opposites. There are also cases where the function is neither even or odd. So you want to make sure that both cases are true or not true. So if the function is not even, do not assume that that means it's odd. Sometimes it can be neither odd or even. Let's go through some examples. So example 1, we got 2x to the power 4 minus 3x squared plus 1. So what you're going to want to do is, I normally like doing f at negative x first because both proofs need it, all right? So then you're going to want to plug in negative x to where. So now what you're going to do is you're going to multiply the negative x by the power of 4. And since this exponent is even, that means whatever is inside the brackets will automatically become positive, because a negative times a negative times a negative times a negative is always positive. So this doesn't change. This also doesn't change. So as you can see, f at x is equal to f at negative x. For it is an even function. Also, if you look, you can see that there's evidence. So this is a even exponent. This is also even. And then it also has a constant term, which odd functions cannot have. Let's prove this one. So let's do f at negative x first. Since our exponents are odd, it will always remain, the negative numbers will always remain negative. So we have negative x at 3, and then we have plus 5x. So is f at x equal to f at minus x? No, it's not. So we have to try again with our other proof. So let's do negative f at x. So negative f at x is negative. And then we got negative x3 plus 5x. So you can see that this sum is equal to this sum. That means negative f at x is equal to f at negative x. Therefore, our function is odd. So, in summary, even functions have line symmetry because changing x to negative x doesn't affect the output. Odd functions have point symmetry because every output changes the sign. The easiest way to classify a polynomial is to substitute negative x into a function and compare the result with the original, which is why I always did negative x first. Alright, now let's move on to the factor theorem. So instead of guessing random roots, we typically use rational root theorem, remainder theorem, factor theorem, and of course synthetic division, but we'll get to that. So all these theorems together efficiently factor polynomial equations. So let's start off with the rational root theorem. So what you're going to want to do is, first of all, you're going to want to figure out the factors of your leading coefficient, will be a, and the factors of your constant term, which in our case would be k. So let's figure it out. What can multiply into 2? 1 and 2. So we'll just write 1 and 2 down here. And then what can multiply into 6? Well, you can either have 1 times 6 or 2 times 3. So 1, 2, 3, 6. So if we list out our possible factors, oh yeah, wait, I forgot to mention it has to be plus and minus. Okay, so now let's list out our possible factors. And 6 divided by 2 is still 3, so I won't write that down. Moving on to remainder theorem. So instead of dividing every time, you can just plug in each possible root into the polynomial. So what you're going to want to do is plug in your roots into the x, both positive and negative, into the x of the polynomials. So, as you can see, when we plugged in 3 into our x's, our equation was equal to 0. Our remainder is now equal to 0 when we plugged in 3 into x, making this our factor. Therefore, our factor would be x minus 3. You recall this equation: polynomial, divisor, quotient, remainder. You'll see that what we have is our polynomial, which is 2, our factor. And now the only thing that we're missing is our quotient, since we already know that this is equal to 0. So this is kind of irrelevant. But we want to find this. So to find our quotient, we must use synthetic division in our leading coefficients of each number here. So if you recall, this number comes from the root of this number, which is our factor, which would just be positive 3. We drag down our value, which will just be 2, and we multiply this by 3, which would be 6. 0. So remember, this is always our remainder. This is our constant value. This is x over 1, not over 1, x to the power of 1, and this is x to the power of 2. So this will be our quotient. So now we can plug that in to our equation. So now you see, we can factor this. So our roots will be, well, if you remember, so the factor theorem tells us our factor, or divisor in this case, which is always linear, which is why we use synthetic division and not long division. So to summarize, the rational root theorem helps us list the possible roots. The remainder theorem lets us test the roots via substitution. And finally, factor theorem allows us to know whenever the remainder is 0. So we found our remainder. The remainder here, using the remainder theorem, is always 0, and this is just our factor. So in summary, our factor is whenever our remainder is 0. So altogether, these ideas allow us to completely factor many polynomial equations. And yep, that is basically it. Thanks for watching. I hope you have a great rest of the year.
Okay, so in this part of the presentation, I'm going to be covering units 4 and 5 of MHF for you. These units introduce some very important concepts in trig, starting with radians and exact trig values, and then moving into graph transformations, real-world applications, trig identities, and finally trig equations. So starting off with the introduction to radians. So most of us are familiar with measuring angles in degrees. So we know one complete circle is 360 degrees, but this year we use radians. So a radian is based on the geometry of a circle. Since the circumference of a circle is 2 pi r, one complete revolution is equal to 2 pi radians, which is equal to 360 degrees. Because of this relationship, we can easily convert between degrees and radians. Some common conversions are 180 degrees equals pi, 90 degrees equals pi over 2, and then 45 degrees equals pi over 4. For example, if we want to convert 135 degrees into radians, we just multiply by pi over 180 degrees. The degrees cancel out, and we're left with 135 pi over 180, which we can simplify to 3 pi over 4. Moving on to special trig ratios. Instead of using a calculator, we memorize the exact values found on the unit circle. And the important values are 30 degrees, 45 degrees, and 60 degrees. So here we have the degrees, we have the radians, and then we have the cos value and sine value. For example, if we had sine 30 degrees, which can also be called sine pi over 6 in radians, we would know it's 1 over 2. If we had cos 60 degrees or cos pi over 3, we would know it's 1 over 2. So, when an angle is located in another quadrant, we use its reference angle, but the sign also depends on the quadrant. So, to determine the sign, we use the cast rule. So, in this quadrant, it's C, A, S, T. C stands for cosine, so the cosine values here are positive, and then everything else is negative. Here, all of them are positive cosine, positive sine, and positive tan. Here it's just sine that's positive, so you can see negative cosine. Then in tan, it's sine and cosine are negative, and then tan is positive. So for example, if we have 5 pi over 6, sine 5 pi over 6, we would use its reference angle. So looking at the unit circle, we know that if we convert it into degrees, it would be 150 degrees, and then we can know that it's just 1 over 2. But you would just use its reference angle by using your special triangles. It's a pi over 6, so yeah, but moving on, our transformations of trig functions. So we have a standard equation, so it's y equals a sine b x minus c plus d. We can use an example such as y equals 2 sine 3 x minus pi over 6 plus 1. Now I would graph it out, but it's a time restriction, so I'm just going to explain what each value is. So our a here is equal to 2, so our a is our amplitude. So the amplitude being 2 means the wave stretches vertically and reaches 2 units above and below its midline. So we have like an equation of the axis, and then it goes 2 above and 2 below. Then we have b, which is equal to 3 here. So b, it calculates the period of it. So basically, we have a formula. So 2 pi over b is the period. So 2 pi, because 2 pi is a full rotation, 360 degrees, it gets back to the same point in 2 pi. So that's the end of its period. So 2 pi over 3 would be our period in this equation. Then we have c is equal to pi over 6. So it's just a shift right pi over 6 units. And then our d is 1, so it's just a shift up 1 unit in the graph. Moving on, trig applications. It's basically the same thing, but it's like real-world scenarios. For example, a Ferris wheel spinning around, and then it's got a height and amplitude. Yeah, and then sound waves, so sine curves and cosine curves look like sound waves, so they can be related. Moving on to cofunction identities. So we know that these identities relate to complementary angles, so meaning two angles who can add up to 90 degrees. For example, we have sine theta equals cosine 90 degrees minus theta, and vice versa, sine 90 degrees minus theta. So these work because complementary angles simply just switch the opposite and adjacent sides of a right triangle. And they're often used to simplify expressions before solving like more difficult problems, especially when you have your unit circle. You'll need it. And then moving on to compound angle formulas. So we have our identities here. So a big one that we looked at all of them. But the compound angle one was a big one for this year because it's about like turning it into a compound angle while it's like just one value. For example, let's use sine 11 pi over 6. Okay, and we'll just solve this using values we know from the unit circles. So if we, or just from, special triangles. So if we have that, we can turn it into sine 2 pi minus pi over 6 because it's equal to 11 pi over 6. And then we would use our identity. We would use sine A minus B. So it's equal to sine A cos B minus cos A sine B. So sine 2 pi cos pi over 6 minus cos 2 pi sine pi over 6. And with our special triangles, we know this is 0 times root 3 over 2 minus 1/2 cos 2 pi sine pi over 6. We have 1/2, and then, this is 1. So it would equal negative 1/2. Yeah, and then on to 5.3, which is identities. Let's solve an identity. So I showed all the identities before and I made a video about it already, but let's just go over one for this. So for example, we have like 1 minus cos squared x over sine x, and it's equal to sine x. So basically we want to look here at our Pythagorean identities because we know when there's a Pythagorean identity and a square is going to be useful. So we know 1 minus cos squared. So if we move this cos squared theta over here, it would be sine squared theta. And we want to get a sine x, so we can turn that into sine squared x over sine x. And it's important to turn it into left side, right side, and then work on the more complicated side. And then try and turn it into the less complicated side. And an identity is just proving that this side does indeed equal this side, and it's just an expanded version of it. So then we're left with this, which we divide it by sine, so it would be sine x. Finally, solving trig equations. It's similar to just solving algebraic equations, but it's just involving trig. So, for example, if we had 2 sine x equals root 3, just keeping it simple, we just move the 2 to the other side, so sine x equals root 3 over 2. We know the reference angle is pi over 3 using our special triangles. this would be x equals 2 pi over 3.
For our advanced functions summative, I'll be going over Unit 6 and 7 covering our rates of change and rational functions units. A rate of change measures how fast a function grows or shrinks. There are two main types of rates of change. Average rate of change, or AROC, is the slope across 2 points on a curve calculated using a secant line, like this green secant line between points A and B on this curve, where the AROC is rise over run, or delta y over delta x of that secant line. An instantaneous rate of change, or IROC, is the slope at exactly 1 point on a curve represented by a tangent line, like the red tangent line at point A. To calculate the IROC, we must use either a chart plugging in values closer and closer to the target x value, or Newton's quotient. For the example, I'll be using Newton's quotient to find the IROC, which is seen right here. And it is equal to the limit of, as h approaches 0, of f of x plus h minus f of x over h. And this works by creating a secant so small that it's essentially 1 point, which is only possible using limits, which is a tool that can let us approach a value without technically equating to it. And this is how Newton's quotient turns a secant line into a tangent line. Now moving to an example. So given the function f of x equals 2 times x plus 3 squared minus 9, find the IROC at x equals negative 3. So the first thing I like to do is set up Newton's quotient. So we set that equal to dy over dx, which is just the proper notation for using Newton's quotient. So then I like to plug in our target value, which is negative 3. So plug that in, and then you can plug in your functions around that. So then we plug in the function 2 times x plus 3 squared minus 9 around what I already subbed in. Oh, this actually should be a negative 3 as well, so write that. And then from there we can simplify. So we can simplify these this negative 3 and positive 3, so these cancel, gives us 0, which you can see in the next line, and then we can also, in the next line, we can also cancel these. So this negative 3 and this positive 3, which in the next line will actually give us 2h squared minus 9 minus negative 9, because this 2 is equal to 0 because it's multiplied by 0. And then we can simplify this further. Negative 9 or negative 9 subtracted is just going to give you positive 9, so then we can cancel out these 9's, which then gives us 2h squared over h. Now we want to get rid of the h on the denominator because we're trying to sub in 0 for h. So if we cancel that out, and we can't sub in h right now because it would be undefined. So we'd cancel those, and then we're left with the limit as h approaches 0 of 2 times h, and then we just sub in 0 for h, which gives us 0. So then we can say dy over dx, plugging in negative 3, is equal to 0. And then this is the instantaneous rate of change of our function at x equals negative 3. Now let's look at composite functions. A composite function feeds the output of one function into another, written as f composed g of x equals f of g of x, as shown here. When combining functions, the result often shares characteristics from its original component function, like x sine x following the bounds of y equals x and y equals negative x. Note that inverse functions undo themselves, leaving you back with your original input, which is shown here. It is also important to note that functions will change to even or odd depending on how they are combined and with what function. And the changes are outlined in this summary chart here. Next, we have rational functions, which follow the general form of f of x equals ax to the m over bx to the n. The key to analyzing them is factoring both the numerator and denominator completely right at the start. There are also a few rules when it comes to analyzing them. You will get a whole at the 0 of any factor that cancels from the numerator and denominator. After canceling, you can find the vertical asymptote by setting the root of the denominator to 0 and solving for x. And to find the x-intercepts, do the same but for the numerator. For the horizontal asymptote, a degree of m equals n means the horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. A degree of m greater than n means no horizontal asymptote, and a degree of m less than n means a horizontal asymptote at y equals 0. And if a root in the denominator has an odd order, it changes signs of infinite. And if a root in the denominator has an even order, it remains the same sign of infinite. When solving rational inequalities, you can never cross-multiply variables because variables can be positive or negative, and cross-multiplying can incorrectly change your inequality sign. Instead, rearrange everything to one side so it compares to 0, find a common denominator, and test intervals using a sign table. Now, let's look at an example that combines all of this together. Given the inequality 0 is less than or equal to x squared minus 6x minus 7 over x squared minus x minus 2, we are asked to identify the key features and solve. So the first step with any rational inequality is to get it to compare to 0. However, this is already done for this inequality, so we don't need to. The only thing that we need to do now is simplify. So the easiest way to simplify this is just by factoring. So we're going to factor the numerator and denominator, giving us x minus 7 times x plus 1 over x plus 2 times x minus 1. And now that this is factored, we can easily solve for the x-intercepts and vertical asymptotes. And earlier, I was saying that to solve for the x-intercepts and vertical asymptotes, you're just going to set each term equal to 0 and solve for x. So solving for x minus 7, you're going to get x is equal to 7. For x plus 1, you're going to get x is equal to negative 1. For x plus 2, you're going to get x is equal to negative 2. For x minus 1, you're going to get x is equal to 1. Now, the next step is to find the horizontal asymptote. So to find the horizontal asymptote, you're going to need to look at the degree of the numerator and denominator. And in our case, it's both going to be 2. And you can see that here as well. So because it's both they're both the same, it's going to be a ratio between the leading coefficient of the numerator and the leading coefficient of the denominator. And in our case, they're both 1. So it's going to be a ratio of 1 to 1 or just 1. So we're going to have a horizontal asymptote at y is equal to 1. Now, we can use our critical points that we solve for, like our x-intercepts and our vertical asymptotes, in our interval table. So we're going to label our interval table from left to right in increasing order, and we're going to have our linear factors on our left. And because we already solved that x minus 7 is going to give you a 0 at x is equal to 7, we can just put that in, and the same thing is true for x is equal to negative 1. So we're going to put that in, 0 right there. And although you can put in zeros for the numerator, for the denominator, they're actually not going to be zeros, they're going to be asymptotes, so you're going to have to put x's where it changes sign. And this is going to be important for when we convert this into interval notation. Now, if we look at the signs for each linear factor, we can see that overall for a function is going to give us a positive here, positive here, positive here, and that's what we're going to be concerned about because we're looking for when the function is greater than or equal to 0. So using those intervals where the function is going to be overall positive, we're going to do our interval notation. So negative infinity to negative 2 exclusive. So exclusive is using the round bracket, and we use the round bracket for vertical asymptotes because it's not going to be actually equal to negative 2, it's only going to approach negative 2. Then we're going to have union to negative 1 inclusive because that's going to be a 0, and we're going to do 1 exclusive, that's another vertical asymptote, union 7 inclusive, infinity. And for infinity, you always use a round bracket because you're never going to actually equal infinity. And that's our final answer. Now, in conclusion, rates of change let us analyze how functions evolve through average and instantaneous rates. Rational functions extend our reach using ratios that introduce asymptotes and holes, and combinations of functions bring it all together by merging simple operations into unified functions.